In this question, we're asked to use undetermined coefficients to find a particular solution to the given differential equation, where the particular solution is the function y sub p of t. Even though this question only asks for a particular solution, we'll actually go ahead and find the general solution using the method of undetermined coefficients. Notice how the given differential equation is a linear second-order non-homogeneous differential equation. The method of undetermined coefficients can be used to find the general solution to a differential equation in this form here, which again is a linear second-order non-homogeneous differential equation. The general solution is in the form given by y of t, where y of t equals y sub c of t plus big Y sub p of t, where y sub c of t is the complementary function, sometimes given as c sub 1 times y sub 1 plus c sub 2 times y sub 2, and big Y sub p of t is called a particular solution. So the general solution of this differential equation consists of the sum of the complementary function and a particular solution. To use the method of undetermined coefficients, the first step is to solve the corresponding homogeneous differential equation by setting g of t equal to 0. The solution to this homogeneous differential equation gives us the complementary function for the general solution of the original non-homogeneous differential equation. And then step 2, we guess a form of a particular solution with undetermined coefficients, which will be big Y sub p of t. And then we'll use that function to perform substitution into the original differential equation and solve for the undetermined coefficients, which will give us a particular solution to the differential equation. And once we have the complementary function and a particular solution, we can find the sum to find the general solution. So again, the first step is to find the corresponding homogeneous differential equation. So setting g of t equal to 0 with the right side equal to 0, we'd have y double prime minus 3y prime plus 5y equals 0. To solve this homogeneous differential equation, we can use the characteristic equation ar squared plus br plus c equals 0, where a is equal to 1, b equals negative 3, and c equals 5. So we'd have r squared minus 3r plus 5 equals 0. And unfortunately this does not factor, so we'll have to use the quadratic formula in order to solve. So we would have r equals negative b would be negative 3 plus or minus the square root of b squared would be the square of negative 3 minus 4 times a, which is 1, times c, which is positive 5, all divided by 2 times a, which is 2 times 1. Simplifying, we have r equals positive 3 plus or minus the square root of, this is going to be 9 minus 20, which equals negative 11, all divided by 2. Notice how the square root of negative 11 is going to be imaginary. So we have r equals 3 halves plus or minus, this is going to be square root of 11 divided by 2i. So because the characteristic equation has two complex solutions, where the form would be alpha plus or minus beta I, notice alpha is equal to 3 halves and beta is equal to square root of 11 divided by 2. So for review, because the characteristic equation had two complex roots or solutions, the general solution to the homogeneous differential equation, which gives us the complementary function of the non-homogeneous differential equation, is going to be in this form here, where again alpha is equal to 3 halves and beta equals square root of 11 divided by 2. Which means we now know y sub c of t is equal to c sub 1 times e raised to the 3 halves t cosine square root of 11 divided by 2t plus c sub 2 e to the 3 halves t times sine of square root of 11 divided by 2t. We'll use this function again later when finding the general solution to the given differential equation. And now step 2, we want to guess the form of a particular solution, which would be the form of a function that would satisfy this differential equation where its second derivative minus 3 times its first derivative plus 5 times the original function would be equal to the linear function 6t plus 2. Some linear function would satisfy this differential equation, which means big Y sub p of t is a linear function with undetermined coefficients, meaning it's in the form of at plus b. If it's helpful, we can refer to this table here to help us determine the form of a particular solution given by big Y sub p of t, where if g of t, the right side of the differential equation, is in one of these forms, we can usually use one of these forms for a particular solution, big Y sub p of t. Before we perform substitution into the differential equation, though, we do have to find the first and second derivative. Let's do this on the next slide. Well, the first derivative is equal to the derivative of at plus b with respect to t, which would just be a. And the second derivative would be the derivative of the constant a with respect to t, which would be 0. So now performing substitution into the original differential equation, we begin with y double prime, which is 0. We have minus 3 times y prime, which is a, and then plus 5 times y, which would be 5 times the quantity at plus b. And this must equal 6t plus 2. Simplifying on the left, we have negative 3a plus 5at plus 5b equals 6t plus 2. Let's write the terms on the left as 5at minus 3a plus 5b equals 6t plus 2. And now equating the coefficients, looking at the t terms on the left and right, notice how this tells us that 5a must equal 6, and these two terms are constants, so negative 3a plus 5b must equal 2. So again, 5a equals 6. Dividing both sides by 5, we know a equals 6/5. And we also know that negative 3a plus 5b must equal 2. Let's substitute 6/5 for a. Negative 3 times 6/5 would be negative 18/5. So negative 18/5 plus 5b equals 2. Let's go ahead and add 18/5 to both sides. So we have 5b, well, 2 is 10/5. 10/5 plus 18/5 would be 28/5. Let's go ahead and multiply both sides by 1/5. That would give us b equals 1/5 times 28/5. So b is equal to 28/25. So now that we know the value of a and the value of b, we know a particular solution. That particular solution is big Y sub p of t equals a, which is 6/5 t, plus b, which would be plus 28/25. So this is actually what this question is asking for, but we can use this particular solution as well as the complementary function to form the general solution given by y of t. But while we're here, let's go ahead and enter y sub p of t. Now this y sub p of t is the same as big Y sub p of t in our notes. So again, the particular solution that we found was y sub p of t equals 6/5 t plus 28/25. Of course, if we wanted to, we could also express this using decimals. But again, let's take the time to form our general solution. The general solution is y of t equals the complementary function plus the particular solution 6/5 t plus 28/25. I hope you found this helpful.